All right, here we go again. Class number 2. Let's record that screen. And then make sure you're over here. You should be able to see my screen. Is that correct? If you can give me a thumbs up, that'd be great. Excellent. Thank you very much. First, a couple announcements. Number 1, if you go to our class website, there is a link to the YouTube playlist. So if you want to, again, revisit the lectures or so forth, you can just click there. As we populate lectures and so forth, you will see more and more videos. So hopefully that helps. Next, as you, I believe you should have gotten an announcement about this on Icon, but if you haven't, homework 1, I did reassign it. I did update the file, basically asking you to install Stan on your local machine and make sure it's installed on the notebook site. Should be hopefully very straightforward. And again, this is the one homework that won't have a couple week lead time. This is a little bit less than 2 weeks to be able to do, but I hope that makes sense for you. And then finally, I know this is Thursday, but we have a small formative assessment to get in the habit of doing them. It'll take you less than 5 minutes. So I ask you fill that out by Monday. I know Monday's a holiday, but literally you could be doing it in class today. I don't care. It's going to take seconds. It's about the syllabus. It's about where you can find me. It's just reinforcing some communication in class. Okay? All right. Then, if we click the link here to go to our notebook site, I will grab the lecture. See if it's up, actually. So today's a great day. I mean, it's always a great day for Bayesian, right? Come on. Who doesn't love Bayesian? Actually, don't answer that. I don't want to know. But that being said, today we're going to cover Introduction to Bayesian Concepts. In fact, I was literally just testing things out, so let me go back to the beginning. Again, you can follow along on the notebook site if you like. Alternatively, there is a link to the PDF of the lecture slides right here on my course website under our date. And if you'd like the lecture files on the GitHub site, they're here. The background reading for this is the Levy and Miss Levy book. Almost sounds like the beginning of a joke. Levy and Miss Levy walked into a bar, something like that. But Levy and Miss Levy, Bob, Miss Levy, Roy Levy, their book on the library's website, this sort of background, basic Bayes stuff. I wouldn't say basic, but stuff that, introductory Bayes stuff is certainly here. One last thing to remember is if you are using the notebook site to follow along for the lecture and everything, if you take notes or you do anything different, don't store it into the class files or class data folder. Make sure it's in your own directory here. Otherwise, class files gets overwritten every time I update the GitHub repo. And then class data is where if we have any data sets to share, that'll be in class data. Okay? All right. Well then, let's get to it then. I'm gonna make this full screen. Okay. Once again, if you wanted to make a PDF of this, under the menu here, under Tools, there's the PDF export mode. So just in case you wanted to see that. But here, I'll dive in. Introduction to Bayesian Concepts, Lecture 1. I got to tell you, I'm a bit nervous. I don't know why, but I'm still, I guess I was nervous the last time too, but now I'm actually having to prove to you that I know Bayesian. Oh boy, that's a tough order, but let's see how this works. So our objectives today are to define what Bayesian happens to be, to talk about posterior distributions, and talk a little bit about Bayesian updating. And if you've never heard about any of that stuff, that's great. If you've heard about all that stuff, thanks for being here and enduring what I'm about to say. But before we begin, this is a picture of me at an old gravesite in London. 2022, I was fortunate enough to take my kids over to Europe. Lisa was teaching a workshop in Mannheim. I got to play dad and take them around, and we have family up in England, so we went over to England, and we all got to pick something we wanted to do in London, and one thing I wanted to do was visit the gravesite of Thomas Bayes. So yes, that's in that background right over here. That's the grave of Thomas Bayes right there. I know that seems a little weird, but let me tell you, in my career as a scientist, I've occasionally proposed grants with Bayesian methods, and I've had some feedback saying, the PI is not a Bayesian scientist or something along those lines. The typical academic, you're not valid or whether you're doing this or whatever. And so from now on, if I ever get a comment like that, this is going in a grant, like appendix. Yes, I am. I went to Babe's gravesite, all right? So that was important to me. But speaking of Thomas Bayes, and speaking of getting into that, actually, I'm going to come back to the slides first. Bayes was born in 1701 in London. His father was a nonconformist minister, so Bayesian already. He's got nonconformist methods. We can think about that. Blah, blah, blah. You can see about that. He was a Presbyterian minister and a mathematician, philosopher. So he had a few things he was doing all the time. And the thing I really wanted to get to is this right here. If you really want to love Bayes, and you have that special person in your life with a small child, why don't you get them this book, Bayesian Probability for Babies. I love this personally. I think it's awesome. I'll give you some pictures here. This is a ball. This is a ball. The ball is a piece of candy on a cookie. Some cookies have candy. Some don't. Take a bite. It has no candy. Did it come from a candy cookie or not? All right? Better yet, it either came from one or didn't. What are the chances? All right? So there we go. It's Bayesian statistics, right? The probability of the bite came from a non-candy cookie, right? Versus the probability of the bite came from a candy cookie. And you can talk about Bayesian updating and so forth going on. So even babies love Bayes. And as I was looking at this year, I noticed we've got a few books for babies that I think would be great. Blockchain for babies, quantum computing, robotics. Any of these valid books. I can't vouch for how good the author is, but I enjoy the spirit. So on that note, let me go back to, oh shoot, I lost my slides. The question I wanted to talk to you about as a class, we sort of talked a little bit about it in introductions last time, but I'd love to just start with a little bit of a discussion that asks you this question. What is Bayesian? So I know we're all remote here, we're all virtual, but I want to hear what you think. What do you think Bayesian, when you hear the word Bayesian, what does it mean to you? And JC. Yep, so you got a prior distribution, something happens, a posterior distribution. Yeah, that's good. Anybody else? Let me think here. What about if I asked you a little bit more about this? You talk about prior distribution. A prior distribution, what does that reflect? What is a prior distribution? What do you think it is? You've probably heard the term, right? That's good. Perfect. Yeah, it's what we know. It's our belief. We come into things with a belief, and Bayesian statistics is a formal mathematical way of taking that belief, quantifying it in terms of uncertainty, right? Each distribution has a range of values that are possible and has a density as to where those possibilities might be more likely than others. So we find a way of quantifying our belief, our uncertainty, and then we put that into an analysis that sort of blends our belief with what we have observed with real data, which also comes from another set of distributions. Now, quick question for you. Do you think Bayesian statistics is something that we objectively, in terms of let me try to phrase this a little better. Excuse me, stumbling over my words. How do you view Bayesian statistics and the idea of belief, which might be subjective, as fitting into the world of science, which is thought to be objective, not subjective? Have you considered any of that? So Bayesian is focused on the subjective part, is what you say. Mm-hmm. Yeah. It's a great point. Yeah, so if I have a prior belief about a distribution, and you have a prior belief about a distribution, and our prior beliefs are different, how does that impact our results, right? So does it now become basically, hey, I think this is the prior. Jonathan's prior is right because look, Jonathan's history, he's been right on priors. Actually, I haven't been right on priors. Actually, you wouldn't want to trust my history. But the big picture is, does it take science, which is supposed to be objective, and turn it into something that's subjective? I think that's the question that you have to think about. Spoken like it's true. What is subjectivity? Great point. This is something where, if you think about it, we have subjectivity in how we design experiments, in how we collect data, in the instruments that we use to do all of that. Although we like to come up with good instruments, whether those are survey tools or fMRI or you name it, like whatever instrumentation is we collect data with. But we also have subjectivity in the models that we run to analyze the data as well, and there's large choice to it. So that's one way of putting it, that while science strives to be objective, subjectivity plays a role in almost everything we do in science. That's a good way of putting it. So Bayes' methods are somewhat similar in that sense. Yes, Sergio. Very good point. So thinking about assumptions, I'm basically, again, repeating everybody what you're saying because I'm trying to make it so your audio doesn't appear on the YouTube channel. But the idea being that in statistics, every model, every analysis we run has a set of assumptions. And you're saying that Bayesian prior subjectivity, prior belief, is just another set of assumptions in that sense. Maybe a little bit stronger than the model themselves. I think that's another good way of putting it, that prior beliefs could be thought of as a series of assumptions about where you think parameters or other values might lie and how you build that into an analysis. I think that's a good point as well. Let me add another point to this. Just because we put a prior distribution and our belief into a prior doesn't necessarily mean that it's so subjective that the whole analysis is subjective itself. So what do I mean by that? Is that if I have a prior distribution that's uniform, right? A uniform distribution. It's a flat PDF, meaning every value in a sample space is equally likely. So if I say, I think the variance of this one model is somewhere between 0 and 100,000. Now, we'd have to assume that the variance doesn't go above 100,000. But that's a prior belief saying the range of the variance. But within that range, all the values of variances might be equal. So that's one way of looking at subjectivity, is now it's not necessarily all subjective or all objective. There's matters of degree, right? A flat prior defining a range is different than if I said, no, this variance follows a gamma distribution where the center of it is around 2, and we have this really steep probability mass around 2. That would be excessively subjective, right? So what I'm trying to argue here is subjectivity in some places is weak, in some places it's strong. And what we're doing when we're in Bayes in the process of picking prior distributions is trying to come up with a quantification of what we know, what we believe, in a way that we can actually show how much belief we have in it, right? If we use what are called uninformative priors, that says we have very little information that we believe about the Bayesian problem. Whereas if we use very informative priors, right, something with a very steep amount of probability mass density over a certain range, it would be very subjective. But there's one other part to it as well, as we're going to see in just a moment. The prior distribution is only one part of the Bayes theorem equation. The other part is the model data likelihood. which sometimes we just call the likelihood itself. It turns out it's the same likelihood function that you build in frequentist statistics and maximum likelihood as well. So that likelihood function multiplies the prior distribution. It turns out that likelihood function involves the data. So if you have a lot of data, that mass of the likelihood function itself will be highly informative relative to your prior. So at some point, your prior distribution becomes less weighted than what your data distribution happens to be, and it matters very little, even with very informative priors. So the other part I'm trying to mention is, even though priors are subjective, data aren't, well, up to the limits of what subjective science happens to be, as was noted earlier. But the data itself are the data, and the model that forms the data likelihood is built with the data as well. So again, thinking that subjectivity is present in the analysis, but as sample size grows, the role of subjectivity diminishes, and it diminishes quite fast depending on the types of analyses or models that you're running. To that point, interestingly, I'm going to tell you this now, it'll come up later in the course as well. Turns out, in maximum likelihood methods, we love maximum likelihood. Who doesn't love a good maximum likelihood estimator, right? Everybody, right? Why do we love maximum likelihood so much? Does anybody want to take a guess why we love maximum likelihood? Because it's straightforward, easy to define, most likely outcome. Those are all valid points. Yes. I'm going to go with another one. We know how it behaves as n goes to infinity. Right? The cold, hard laws of math, like I say, sometimes the math don't care, logic, is that we can show under certain conditions that are usually met by our data analyses, that as our sample size goes to infinity, our maximum likelihood estimator converges in distribution to a normal distribution, converges in probability to the true point estimate of the parameter itself, and is the most efficient estimator in terms of the amount of variance around it as well. Those are three of the grid properties of MLE. Well, it turns out, as I mentioned earlier, if maximum likelihood shares the model data likelihood with Bayes, those maximum likelihood properties apply to Bayes as well too. So in the limit, as an estimator, as a Bayesian estimator goes, as n goes to infinity under certain, what we call regularity conditions, the same properties hold. That our posterior distributions become normally distributed, converge in distribution to normal. The point estimate, or the mean of that, converges with probability 1 to the true value. They're not as asymptotically efficient, well, it could be more efficient, could be less efficient, depending on the balance of what your prior is, could be versus your data. But generally speaking, the same good properties about maximum likelihood hold in Bayes as well too. So I look at Bayesian as a way of doing maximum likelihood with a little bit more information. And in some cases, in particular in psychometric models, that's important. I don't think I led with this in our previous class meeting, but I was originally Bayesian not because I was a full-blooded member of the Bayesian cult, which I am now. I went through, when you go to Bayes' grave, you go through the initiation, right? I mean, that's sort of right there. There you go. Totally a Bayes member now. But I was a Bayesian because I had to estimate models. I think I did say this actually. I had to estimate latent variable models with some 30-odd latent variables, 36. I remember I ran a model with 36 latent variables in 450,000 cases. And I couldn't get it to run in any software that I had learned how to use to that point. But I figured out how to get it to run with a Bayesian estimator. So Bayesian, in terms of optimization, in terms of estimation, can take a very hard problem that's in maximum likelihood, particularly in psychometrics. In psychometrics, when we have non-normal data, we have a problem in estimation. We have to integrate out latent variables. Otherwise, our likelihood functions don't have those good properties that ML statistics have. And one of the remedies to that is putting it in the Bayesian context, because the Bayesian context, the number of calculations needed grows linearly with the number of latent variables as the number of latent variables grows, whereas in an MLE approach, it grows exponentially. So there becomes a crossover point to where the number of calculations gets smaller in Bayes. Anyway, too much information. This is a great conversation. Bayes is all around us, but no. Anyway, this is where I think when we talk, one last note about what Bayes is, we talk about the brain being a Bayesian, right? Biases, beliefs, assumptions, all of us have that. That's how our brains are formed. It's how we, can go through life and not have to overthink every situation in what we do. But our brains quickly adapt to new data as well, right? I was driving home from my Oakdale office the other day, and at a green light, I was making a left turn that I was supposed to yield, and another car across the street decided to stop, but it was a two-way green street, and I'm like, wait a minute, they've got a green light. If I turn, or do they? I don't know. And they're waving me on. I'm like, oh, I don't know. So quickly, my belief and my assumption, which is they should be going, changed to adapt to the situation of them waving me on, which was still a little weird, and I don't like doing, but anyway, drivers. Bayesian is ineffectively, I'm a Bayesian driver, let's put it that way. But then I adapt to data and I use my horn. I know I'm not a Midwesterner, I use the horn. So, all right, enough of this. Any other questions, any thoughts about the Bayesian idea, just to get us started? This is the closest I get to a class that's not the quantitative technical classes I'm used to teaching, where we sit around and talk about our feelings about things. This is the closest I get. But that's only because the prior distribution has Bayes. Yes, JC. Great question. So yeah, when do we use Bayesian methods is a question that we all struggle with. In fact, struggling with it, how do we teach it as a curriculum? Where do we enter it? Right now, it's one of our last classes in the curriculum. I know there's a cross-listed undergraduate class as well with the stat department. So generally speaking, I find Bayesian to be useful in several cases. Small sample sizes, you mentioned, would be one. And the reason for that is in small sample sizes, particularly in psychometric models, convergence can be an issue with maximum likelihood. But it turns out Bayesian methods with the prior distribution, when you can put a little bit more certainty about certain parameters, will converge in times where maximum likelihood sometimes won't, particularly in small sample sizes. So that's one good place. Another good place for Bayesian methods would be whenever you have a prior belief, if you're updating that belief, if you're trying to change or adapt to new data, a new condition or so forth, Bayesian methods are good for that as well. And then high dimensional data analyses, I find Bayesian methods to be very good for as well too. Generally speaking though, for most of what you do, Bayesian is sort of an option. It can be, for instance, if you're using for the package M+, and you don't specify Bayes and your model breaks, usually the remedy is, try Bayes, and it fixes it, right? So Bayesian, for I think a lot of people in practice, is slower, harder, more challenging to implement. And so what you'll see is it's only implemented as a system of last resort. But I like using Bayes in my work for the small sample sizes, or if I'm like for some of my work, I try to track learning across an academic year, and I might want to update what a student's profile of skills or knowledge happens to be. Bayesian is what I use for that as well too. I hope that answers your question. How did I do? Thank you for the question. Any other questions? Okay. And for the record, I would make a terrible instructor of something that's not like equation based. I'm like, oh, you think that? That's great. All right, moving on. Next. How do we feel about Bayes? Not going to be me. All right, so let's talk a little bit about the basics of Bayesian analysis. Bayesian statistical analysis refers to the use of models where some or all of the parameters are treated as random components. So let's talk a little bit about what this means. Analysis. That means taking data and putting it into a model and estimating the model itself, not usually using hand calculations. Parameters are the model terms that are unknown that you seek to estimate. So if you have a linear regression, what are the parameters? It turns out each of the betas, each of the coefficients, regression coefficients, are a parameter, and your residual variance. So in Bayesian analysis, I mentioned all or some parameters treated as random. The idea of a prior distribution is the idea that a parameter actually is random. It comes from this sample space that might have a different density to it. And so that definition of random happens to be there. In cases where, in this class, we are going to treat everything, every parameter as random. So we call this a fully Bayesian approach. I'm going to contrast that with an approach where only some parameters are random. So for instance, item response theory. In item response theory, I'll keep it simple. There's a one parameter model. It has a parameter for every item called the item difficulty. And then every person has a parameter called ability, theta, B, whatever you want to call it. B for difficulty, theta for person ability, we can call it that. In a traditional item response theory setup, we often make an assumption about the distribution of ability. Now, if you're a Roche modeler, you might do things a little bit differently. But let's talk about, well, that's a different cult. And let me tell you, that can only be part of so many different cults. So I'm part of the Bayes cult, but not the Roche cult, all right? But the ability distribution is usually set to be standardized, standard normal, right? Does this seem to ring for those of you who've done IRT, right? So now we've got a person parameter that we say, oh, that follows a normal distribution. That's a prior distribution. The person parameters are random, but each item parameter B might be fixed. So if we run to M+, or IRT Pro, or I'm blanking on the term now. It's the one that's superseded IRT Pro that everybody uses. Anyway, FlexMert, gosh. Run to that and you implement this model, it's going to have a prior to it. It's partially Bayesian, sort of. And why I say sort of is because you put the prior there, but if you use most ML methods, it integrates over the distribution that was random. Similar features happen under factor analysis. Similar feature happen under multi-level models, right? In multi-level models, you often start with the idea of a random intercept. The term random is in the name, right? It's literally a random intercept. Turns out that Roche model I told you about is a random intercept model also. Or that one parameter IRT model is a random intercept as well. So you see quite often in statistics, partially Bayesian models almost everywhere you go. And the distinction that I'm trying to make here is, in our class, we're going to specify a prior for all the models. When you use Stan, you can't easily just... You can. Actually, Stan's quite in depth. But for what I'm going to teach, it's all going to be every parameter has a distribution. Fully Bayesian is what we say. Cool? All right. So each parameter has some type of distribution. So the likelihood function of the data, so that's... Now, the parameter distributions we often call prior. The likelihood function of the data itself is our model, right? So each model that we specify, a linear model, a factor analysis, an IRT model, you name it, all the model classes that we describe have a likelihood function. Believe it or not, even classical test theory, you can derive a likelihood function for a test score. You may not have thought about that before, but it falls under factor analysis, believe it or not. So all of these has a likelihood function. The data, the model itself forms the model data likelihood. And then that likelihood gets augmented with an additional term that represents the likelihood of the prior for each parameter. So when you think of the entire likelihood function itself, every parameter with the prior is going to multiply that based on where that value of the parameter happens to be. Happens to be in the sample space. How are we doing so far? Okay. And the key in thinking this is when we have a parameter and the process that we're going to go about to estimate it, although not today, that'll be next week or the week following. The process of estimation basically is trying out whether a parameter should be allowed or not. It's using this random process to say, hey, I want to sample this number. Is it a really valid number to take based on my prior and my likelihood, or is it not? So when you think about prior distributions, what we're really specifying is parameters that are much more likely to be included in our analysis as we go forward. So this is like saying each parameter has a certain likelihood. So likelihood is a term that we use in statistics. We usually have a likelihood function. For us, likelihood will also be synonymous with height. When you think of a prior distribution, actually, let me see if I can this. So if you have a distribution here, let's say this is a parameter, we'll call it beta 0. We'll call it the intercept of a basic linear regression, right? And let's imagine we have a prior distribution on it. Hey, that looks somewhat normal. Probably not exactly, but that looks normal enough, right? Right. So this term on the y-axis is what we would call the relative frequency, right? Sometimes the height, right? So if we try out a beta 0 right here, that would be its relative frequency, but this is also the likelihood right here. So y, basically the height of the distribution, or if we provide beta 0 into the distribution function, the PDF that gives us this shape, it tells us the height. That tells us how likely things happen to be. So when you're at a tail of a distribution, like if we picked a parameter here and we compare it with a parameter here, the parameter with the higher part of the curve is more likely to have occurred. That's all we're saying. So when I say likelihood, when I say distributions, this is what I'm referring to. I hope that helps give a little picture to it. How are we doing so far? Okay. So the final estimates of this whole process are then considered summaries of the posterior distribution of the parameter. So what ends up happening is we take the prior distribution, or distributions, we take our model data likelihood, we go through an estimation process, and what we end up having is yet another distribution. Right? So here we go from beta 0. If we talk about this, I'll call this beta 0 hat. Right? This thing might look like this right here. Right? So our prior distribution thought it was here. What we end up getting is a posterior distribution. Posterior distribution. Right there. Right? So we are left with a posterior distribution. So often what we end up doing is summarizing this to get a parameter point estimate. Right? This right here might be its mean, right? This would be the mean of the beta hat distribution, posterior distribution. The mean has a very specific term. I'll tell you it now. We'll revisit it later. It's called EAP, expected a posteriori is what that means. Expected meaning expectation, a synonym of mean, the sort of expected value of a distribution. But that's not the only distribution that we can summarize it with. We can talk about standard deviation. We could also talk about median. Median, right? Or even mode. Actually, median would be here. Mode would be there. Anyway, getting my skewness strong. So, posterior distribution shows up, but then we have to summarize it. So when every parameter is random, and we start with the belief of a prior distribution for it, the end of the process is an updated version of that belief, and that's called the posterior distribution. And it usually shifts the prior to something different. So, in practice, then, we summarize the posterior distribution using its mean, standard deviation, or other values that make it quantify it easily. And those are the parameter estimates that we report. Right? All right. Whenever you were in linear models and you use the least squares estimate, you would get beta hat for each of your coefficients. For us, we would use the mean of their posterior distributions as the coefficients. In linear models, you could show that sigma squared times your design matrix transpose itself, or x transpose x inverse, that is your residual variance, or residual, your mean square error, sometimes called that. In Bayesian statistics, we would find a posterior distribution for that and get its mean for it. Any questions? All right. So why do we use Bayesian? This relates to some of the questions, the question from previously. They get used because the relative accessibility of one estimation method. And I say relative accessibility because, as you're going to find out in this class, STAN takes effort. STAN takes time. Estimation takes, you have to build a lot more detail into your analysis. And that estimation method is called MCMC, or short Markov chain Monte Carlo. If you are in some of the hard sciences, physics, engineering, you might just call this Monte Carlo as well. The Monte Carlo refers to it being a random process. Usually that term, it refers to classical gambling statistics in Monte Carlo and roulette wheel and so forth, but this is sort of the idea that it's a random process. And there are four, to me, I tried to outline four main reasons. We've got missing data. Actually, missing data methods are great. If you have missing data, Bayesian is good for it because there is no easy solution to missing data. And the bad solutions all forget that there's error, like sort of make a prediction of what an observation should have been without any error to it. Bayesian methods are great for missing data. You may have a lack of software capable of handling large size analysis. I know you laugh at that when you think of that we're in the time of large language models with trillions of parameters and so forth, but good luck. Good luck getting a small model to run. Here, I'll give you one. Take a 10-dimensional factor analysis using categorical data or 10-dimensional MERT model. Good luck running that with something that's not Bayes. Probably isn't going to go well. I guess limited information may go a little bit better, but even that starts acting weird after a while. The other thing that Bayes does, because the software is so general, is if you come up with a new way of estimating a model, or you come up with a new model altogether, you can put it in and estimate it in a very well-founded, well-rationed statistical framework, estimation framework. So for me, in the early 2000s, that's where I was. We had this new psychometric model, a diagnostic model. It was called the fusion model. It sounds so exciting. Fusion, yeah. And turned out it was a mess. We had to estimate it with Markov chain Monte Carlo. At the time, Markov chain Monte Carlo was very new. And I will tell you, my RA, I was really lucky to have, basically said, oh, you know how to code, right? Well, here's some Fortran code with this model. Oh, you don't know anything about MCMC? That's fine. Just read the code and you'll learn it. It's no big deal. Oh, and you don't know anything about the model either? Just read the code. It'll be fine. So it's this very weird world. But each of you is creative. Each of you is thoughtful. Each of you knows the limitation of certain models. If you want to extend a model or generalize it into a different way, Bayes is your friend. You can easily do that and estimate it. And finally, the last reason, if you are a philosophical, and I have a typo, sorry, philosophical reasons, shouldn't be a Y there. The philosophical reasons are the membership of the cult of Bayes, right? That you really believe that prior belief is important in analyses, want to quantify it, want to grab a better sense of uncertainty. You may actually, for me, part of my membership in the cult, I'll just admit I'm a full-fledged member these days, is I love the quantification of uncertainty in the posterior distribution. A lot of times, particularly in psychometrics, particularly in large-scale assessment, let's put it that way, right? Go to NCME, the National Council on Measurement and Education, that conference. You will see analyses done all the time where they take latent variable scores and they forget that they're measured with error. And they do them in secondary analyses or anything else. It's like, what? What error? Huh? Error? What's that? Well, it turns out in Bayes, you know what error is, or you know what uncertainty is, because the posterior distribution quantifies it. So it's a good way of for me, that's why I like the Bayesian methods. We have a very straightforward accounting of how we handle error and how we can use that in subsequent analyses. Questions? Thoughts? Nah. All right. So there are some issues with Bayes, though. The use of Bayesian statistics historically has been controversial. But I would say you are reaching it at a time where it is almost not controversial at all. In fact, it's almost becoming a standard matter of practice. The controversy came from the use of subjective judgment, right? We talked about that in our early discussion about what Bayes means. But literally, in my early days of writing papers, people would talk about the papers just being bad overall because they use Bayesian methods. Even if our prior distributions were as uninformative as possible to make an analysis run, it was just a bad idea to use anything subjective in an analysis. Those ideas have weakened, thankfully. Additionally, one of the barriers or one of the issues with using methods, if you're using Markov chain Monte Carlo, is that they are computationally intensive. They take a long time to run relative to frequentist analysis on basic models. And until very recently, very few methods were available for those of you who weren't fluent in Fortran, C, or C++. Right? Thankfully, even in the 90s, we had bugs. Bayesian updating by Gibbs sampling. It was a program. It became WinBugs. JAGS, just another Gibbs sampler, took over after that. And then more recently, Stan plus M plus has Bayesian implementation. I hear Stata has some too as well. So Bayesian methods are much more accessible now, but they still take a long time to run. And finally, understanding of what Bayesian methods has been. Like mathematical statistics came to Bayes methods long before much of what we do in application does. And so understanding what they are has been slow. Thankfully, again, that's changing. And in the last 20, 25 years, you see Bayesian methods widespread in education, quantitative methods in social science. So Bayesian is much more familiar now. You're coming to it at a very good time. When in the early days, I feel like I was not really in the early days. I mean, Thomas Bayes lived in the 1700s, but the pairing of Markov chain Monte Carlo and computation came to statistics in the 90s, and then education and social science a little bit after that. That's where I grew up. It was really difficult compared to now. Things are much easier in Bayes now. One other thing I forgot to mention. When I mentioned estimation and Bayesian, not all Bayesian methods need MCMC to estimate it. MCMC is one type of estimator for Bayesian methods. What we're going to do today, about in a few slides, is going to be non-MCMC. So just remember that as well. But then we're going to quickly not use anything but MCMC as we go forward, okay? So just as a note, Bayesian does not mean MCMC, right? But MCMC is a Bayesian method. So how's that sound? Okay. So here's how Bayesian statistics work. Let's imagine we were after the probability of an event A occurring conditional on an event B itself. What Bayes' theorem gives us is sort of what we write out here is the probability of B occurring given A times the prior probability of A occurring over the probability of B occurring itself. And if you want to know where this comes from, if you look at like a 2x2 table of counts, and you want to, or zeros and ones, and you want to talk about the probability of each cell, right? You can sort of trace out Bayes' theorem looking at the margins, which are probability A, probability B, versus one of the conditional statements, probability B given A itself. You can sort of see where the numbers come from. Oftentimes, we write this with this term right here, which means is proportional to, right? And we have the numerator listed on the other side of it. Why we say it's proportional to is if we look at this probability of B, in statistics, we sometimes call this a normalizing constant. A normalizing constant is something that doesn't vary. I mean, it's conditioned, right? We have that marginal distribution of the parameter itself, or in the data, or however you want to talk about it. Here, normalizing means it's just there so that the result is a proper density function itself, or distribution. A proper distribution, a continuous distribution, is one that integrates to 1 across its space, and a discrete distribution is one where the discrete cells, the mass of those discrete cells, sum to 1. So this term often gets omitted. We call this proportional to itself. Now, any questions on what I just said so far? All right. Let's go through this one by one. The term here, P of A, the probability of event A, is the prior distribution itself. So if we had a prior distribution of how many cookies had chocolate chips in them, right, or M&Ms in them with candy, that's it right there. That's our probability, our density. All right? P of B is the marginal distribution, in this case, of what we're going to call the data later on. It's the probability of B occurring overall, not conditional on A, just overall. The probability of B given A is the conditional distribution of B given A, and where we are going, this is going to be our model data likelihood. This is where the data comes in, right? And finally, the probability of A given B is now the updated distribution. Right? So we start with a belief distribution of A, that's our prior. And then once we're done with this process, we've updated our belief to be a posterior now that we're given the result B itself. So that's our Bayesian statistics quick overview. Questions on this? So once again, prior right here, posterior right here, and model data likelihood right there. Those are the key terms that we get in there. All right, let's talk about a live example here. Let's imagine I had a die. And when I taught this class the last time, I actually brought a die to class, but you just pretend. Here is one single 6-sided die, right? Numbers 1, 2, 3, 4, 5, 6. I roll it, it lands with one number up. That's the number I take. And let's say we're looking for the probability of rolling a 1 on that 6-sided die, right? This is the worst game of craps that you'll ever see. All right, those of you who gamble. Remember, Bayesians are gamblers, sort of. Right? Anyway, never mind. The probability that the die has a 1 on it when we roll it is P1. Let's imagine we then collect a sample of data. We roll the die 5 times, and sure enough, 3 out of 5 times a 1 appears. That's pretty amazing. All right? And let's assume that those are independent tosses, so each roll does not depend on the roll before it. Then the posterior distribution of the probability of rolling the notation for it is this: the probability of observing a 1, or the likelihood of observing this probability conditional on our data itself. And we can calculate that again via Bayes' theorem. So our parameter of interest is the probability we roll a 1 on this die roll. And x is a 0 if we roll something other than a 1, and x is a 1 if we rolled a 1. So what we can assess is now this is a little weird. We have a probability of a die being 1, and in this notation, it's the probability function, or the density. Right? This is usually used to denote a discrete probability. I more often use the little letter f to describe this as a function. This term is now a posterior distribution of where we believe that probability to lie. So remember, a probability ranges between 0 and 1. What we would envision with this, if we were to draw a number line between 0 and 1 with decimal values between there and graph it, we would see a shape of a likelihood function where we would be most certain in certain ranges and not certain in the others as well. Questions on any of these? Okay. So let's define this likelihood function a bit more. When I phrase the problem of rolling a 6-sided die and observing a 1 versus not, it now doesn't become the distribution that we would use. We have to pick a distribution for the data. And it turns out there's 2 outcomes, right? I either observed a 1 or I didn't. Anybody know of a distribution we can use for 2 outcomes, binary data? A Bernoulli distribution, correct, right? So a Bernoulli distribution, the density function looks like that right there. The probability mass function is sometimes called. It's a discrete distribution. The probability of observing event in this case is P1, rolling a 1. It's raised the number of times we observed it, or in this case, whether or not that roll was observed. And then 1 minus P1 is raised to the opposite, the complement. The probability we didn't observe a 1 raised to the number of times we didn't observe a 1. Now this product shows up because we assumed that all the rolls were independent. When we talk about independence in statistics, we implement that using a likelihood function with the product. Basically, if these rolls are independent, that means their densities should multiply to provide the overall distribution likelihood itself. So there we have it. I said all these things. So this is the likelihood function. This is without any prior itself. But remember, actually, this is the log likelihood. Remember, this is the probability we would roll a 1 with our just given our data itself. And I went and calculated this for all values of probability between 0 and 1 in, I think, 0.01 increments. And this is where we would find, this is our likelihood function. Where would you find, if this was a maximum likelihood estimate, we would find the maximum of this function, which is somewhere around here, draw a line down, and that would be our estimate of what P1 happened to be. And actually, in this case, we had 3 1s and 2 not 1s, so that would be 0.6. That maximum should be right about 0.6 in this case. Turns out the mean is an easy MLE for this distribution. So far, so good? Okay. So let's now define a prior distribution for it, though, because we all know we should have at least some type of belief in the prior, right? So this prior distribution of P1, again, I'm using this P notation, even though it's a little weird because this is a continuous measure. We're looking for a distribution that describes our belief around that number line between 0 and 1. Where do we believe this should be, right? Just off the top of your head, if I'm rolling a fair die, we would expect this distribution to be centered around 1/6, meaning there are 6 sides to the die. If it's fair, they should all be equally likely to appear. So therefore, 1/6 should be the center of my likelihood, my probability density for my belief. But you might want to realize that I don't always bring a fair die. In fact, when I came in the last time to teach class, I had a loaded die, and it kept rolling 1s. So it's like, oh, am I playing a joke on you? You don't know, right? So you might want to leave some uncertainty for a number that might not be 1/6, because you know your instructor likes to change things up a bit. So let's consider something called the beta distribution. How many of you have heard of a beta distribution before? Beta, kind of an interesting distribution, has 2 parameters. Unfortunately, one of them is often called beta as well. We have an alpha parameter and a beta parameter. Those 2 parameters describe the shape of the distribution itself. Whenever you start looking into distributions, the first thing to do, for priors, the first thing to do is a prior distribution needs to match the range of the parameter it's being applied to. Oftentimes, in a distribution language, the distribution itself is defined on what we call a sample space, meaning it's valid under these numbers, right? So, first of all, our probability, we know, has to be between 0 and 1. Otherwise, it's not a probability. So we need a prior distribution that follows that same range. The sample space of the prior has to be between 0 and 1. So what do? We look up all the distributions that are defined on 0 to 1, and we come up with one. Beta happens to be defined in the space between 0 and 1. It has 2 parameters that govern its shape, its spread, its location itself, alpha, beta. So this is the beta distribution itself right there. This term on the bottom is the beta function, not to be confused with the beta distribution. And the beta function depends on another function called the gamma function, and there's an integral. And if you remember this stuff, good luck. Good for you, because I don't. This is not going to be on the test or the quiz. This is just noting, to get this prior distribution, we need a couple other definitions to be able to get there. And if you've taken a mathematical statistics class, if you lived in math stat for a while, this beta distribution is like your first challenge in a distribution course. It's a mess to work with, but it's just a lovely distribution after that to implement. I don't know about that. Distributions being lovely. There's some subjective belief for you. All right. Okay. So more on the beta distribution. Number one, the beta distribution's mean is alpha over alpha plus beta. Right? Remember, alpha and beta are those parameters. Those parameters are real numbers that are positive, right? They have to be, and there's certain ranges to them as well too. That turns out the parameters of the prior distribution get a special term in Bayesian. We call these hyperparameters. You know, science has reached a level up when you put the word hyper there, right? Anyway, hyperparameters are the distributional parameters of the prior distribution themselves. Okay? So that differentiates them from the parameter of our model. In our model that we're trying to implement here, we have one parameter. It's the probability of rolling a 1. That's just a parameter. The prior distribution, we pick its hyperparameters in this case, alpha and beta. right? We can pick values of alpha and beta to correspond to 1/6, right? So for instance, if I picked an alpha of 1 and beta of 5, the mean of my prior distribution will be 1/6 because of alpha over alpha plus beta. Similarly, I could pick alpha to be 100 and beta to be 500. That would also give me a mean of 1/6. But one of these choices is more informative than the other, right? If we have strong beliefs, we would want a prior distribution that has a very focused amount of mass around 1/6. If our beliefs are weak, if we don't exactly know, basically what you have to ask yourself is, what's the chance that Jonathan Templin uses a loaded die in my example in Bayes, right? That would be one where you'd have to work differently. So let's talk about the differences. We have to talk about the variance or the spread of the beta distribution. And that's this ugly looking function, alpha times beta over alpha plus beta squared times alpha plus beta plus 1. By the way, you don't need to memorize this. I had to look this up. You can look this up on your own. Just know it exists, right? So if we were to use an alpha of 1 and beta of 5, we get a mean over prior distribution of 1/6 and a variance of 0.02. Now that you cannot tell in absence of any other numbers whether that's informative or uninformative. Right, the variance of 0.02 is quite small, but remember the range of the parameter is quite small. It's between 0 and 1. If we use an alpha of 100 and a beta of 500, our mean is still 1/6, but our variance is, I believe, 100 times smaller. 0.0002, right? So now, if you were to describe which one quantifies a strong belief relative to a weak belief, choosing the larger alpha and beta is a strong belief. It has very small variance in the prior distribution, whereas alpha of 1 and beta of 5 has a much larger variance relative to it. So we define a prior with a smaller variance as being more informative, whereas informative priors are those with relatively small variances. Uninformative priors have large variances. Sometimes we use the word diffuse to describe uninformative prior, and I'll describe why that is in just a second here. In fact, it's right here. So here's a plot of these two prior distributions. The black line is our uninformative prior. Turns out the mean is actually still right here, 1/6. But you can see how spread it is, right? Remember, the height of this line talks about where our certainty lies. And that certainty lies in a pretty big range, pretty high up, not close to 0, literally between 0 and almost like 0.4, right? It's unlikely we find a 0.4 relative to something lower below. However, it's possible. Whereas look at the dashed red line. That's the informative prior. Where that thing is close to 0, the prior itself is going to have a big role. Think of it this way. Let me go back a couple slides. Our Bayes theorem equation multiplies our model data likelihood by the prior. In this case, I haven't taken a log density of any of this. If our prior distribution gives us a number, returns a number that's close to 0, guess what happens to this likelihood? It gets zeroed out. So a super informative prior is a prior of 0, meaning it can't happen. Sometimes we call it degenerate in that case. So when you look at this plot of the dashed red line, all the places where this line is 0, we're likely to not find a parameter estimate at all, right? It's going to shut down the range of our posterior distribution. Whereas the black line has a much wider spot that's not close to 0. It takes to about 0.6 to get close to 0 on the black line. Questions on any of this right here? Okay. So, turns out there's another reason to choose a prior for P1. A better reason, an even more convenient reason to choose a beta prior for P1. When combined with Bernoulli or binomial data, Like the model data likelihood is of a Bernoulli or binomial distribution. It turns out the beta as a prior with Bernoulli or binomial as data combine to give us a posterior distribution that we can derive analytically. We can mathematically provide a derivation for it. And it turns out that posterior distribution is also a beta distribution. Right? So why that's convenient, actually, here what we can say is that beta distribution will have the posterior distribution of beta will have an alpha parameter that's the prior distribution's alpha plus the sum of occurrences of seeing a die of 1. The beta distribution, the beta parameter of the posterior distribution, remember this is after you've observed my die roll, is the beta parameter of the prior, which I'm calling B in this slide, plus the number of times you didn't observe a 1. So we can easily estimate a posterior distribution in this very small example. It also has another name. When you pick a prior distribution that matches the shape or the family of the posterior distribution, so in our case, prior distribution is beta, and we can derive the posterior distribution being beta, we end up with what's called a conjugate prior. Again, a conjugate prior, this is an important definition, a conjugate prior is a prior distribution such that the prior and the posterior come from the same family. So if you have a normal prior, you get a normal posterior, that happens. Right? So here, our prior is beta, our posterior is beta. Now, how would we figure that out? Well, it turns out you go back to Bayes' theorem, you plug in each of the mathematical formulae for each of the forms that you have there, and you do some algebra, calculus, derive the posterior, and then redefine its shape. Conjugate priors are convenient. They're super easy to work with. They often lead to results that don't have to be estimated iteratively, and they're easy for description. Some of the other big families of conjugate priors, if you run a Bayesian linear model, right? Again, a regression ANOVA model, if you put a normal prior on the coefficients, the posterior distribution is also normal. So it turns out you can use a Bayesian update, easy, quick Bayesian update to get that. Same thing with the variance. Blanking on it. I think it's inverse gamma provides a inverse gamma distribution for the variance in that case as well. But that being said, the conjugate prior no longer is. It used to be a really important part, particularly before computers were used. I mean, I know it sounds. None of our lifetimes, computers got invented before any of us were born. Connection refused. Oh, that's fun. I'll have to come back to that in just a bit. Computers were used built long before any of us were born. But remember, Bayesian statistics has been around since the 1700s, right? So the issue with conjugate priors used to be that to use Bayesian, you really needed a conjugate prior without a computer. Since the advent of computers and Markov chain Monte Carlo, we don't need a conjugate prior. We can always sample or create the posterior distribution as we go. So it's less important now as we go forward. The other part where you'll hear the word conjugate prior is there's one Markov chain Monte Carlo algorithm called Gibbs sampling that relies upon the Markov chain Monte Carlo. It's the prior distribution being conjugate. Gibbs sampling draws directly from the posterior distribution. It never rejects draws. These are things we're going to talk about in a few weeks, so just giving you the foreshadowing right now. You don't have to remember this. But conjugate prior, really good for examples, really good for the basic Bayes, but not needed for everything else we do. Cool? Cool. So once you put prior and data together, though, take a look at our distribution. This is our posterior distribution right here. Right? So now the black line again is our uninformed of the prior. Remember there was 5 data points, with 3 1s and 2 0s, right? So here how would we summarize these two distributions? Right? Well, we would take their mean, their EAP estimate. And so if you use the informative prior, your mean's still somewhere around 1/6. If you use the uninformative prior, your mean is somewhere around like 0.35 or so. So between the two of those, what you end up getting is a choice. Like, which one seems better? I don't know, right? How would you know? And here's the subjectivity that goes into it. Which one do you believe is better? Well, it depends. And again, it depends on whether or not I'm using a fair die or not, right? If you use the uninformative prior, you would say there's a high chance that probability is far away from 0.18. Right? In fact, you can summarize its mean. You can talk about standard deviation. It's sort of where the quantiles of the distribution happen to be, percentiles and so forth. Whereas if you use the informative prior, you say, yeah, very small chance still. Right? So what this leaves you is ambiguity. You have no idea whether I'm using a fair die or not. Right? All right. So Bayesian estimates themselves are summaries of this posterior distribution, as I just mentioned. So I calculated some of these summaries. So with hyperparameters 1 and 5, the mean, the point estimate, the EAP estimate, turned out to be 0.36. Right? And I calculated it based on the conjugate prior idea. The standard deviation of that estimate was 0.138, kind of wide. With the hyperparameters 100 and 500, the mean was 0.17 and the standard deviation was 0.05. So widely different data. And again, this is part of the explanation I was talking about, the role of subjectivity. In the uninformative prior case, right here, we get a result that's very different than the informative prior case, right? Who's correct? How would you know? Nobody would know. If this was just a live experiment, you couldn't. And this is the role of subjectivity in the analysis. It takes precedent, particularly for what we have in this case. We have 5 observations of data. But as the number of observations increases, the subjectivity disappears. And you can even see that happening in our calculation of what this ratio happens to be. Right? When we have a handful of cases, we add to it a 1 in the numerator and a 5 in the denominator. Those are the hyperparameters, right? It doesn't take long before the number of cases exceeds the number of hyperparameters we have, right? But if we start off with a 100 versus a 500 in the numerator and the denominator, it would take quite some time to observe enough data to overwhelm what the prior would be as well, too. So there's this interplay in Bayesian statistics between knowledge that your subjectivity is higher when you have smaller amounts of data and understanding what you're trying to do with your design, your experimental design or your study itself, right? If I were trying to describe, election behavior, this is something different. But this is the part that is fun to me, though. We can still use Bayesian statistics to our benefit. I can't see what's down there. The standard deviation is analogous. Hang on, I can't get smaller. I'm sorry, that got cut off. The standard deviation is analogous to the standard error in frequentist statistics. That's really what I wanted to say here. So when you get a frequentist statistic and you look at its standard error, where does that come from? It comes from asymptotic theory, ML statistic, right? So in each of the parameters in maximum likelihood, you run a linear model again. Take the LM function in R. You get coefficients and standard errors. Like, Jonathan, I got standard errors. I've got uncertainty. Why do I need Bayes? Turns out those standard errors are based on assumption. They're the asymptotic distribution of your parameter as n goes to infinity. But unless you're, have more talent than I realize, who has an infinite sample size? Right? Nobody. So what do we do in that case? Good luck. It's hard to tell. It may or may not be appropriate. It all depends on the asymptotic convergence of your sample. So Bayesian sort of tries to quantify uncertainty not under asymptotic convergence. But moving forward. There is one more thing we can do. Particularly in this case, we can do something called Bayesian updating. So maybe I rolled the die 5 times because this is a hour and 15-minute course. That's 5 observations. But I don't have to stop there. I can keep adding rolls of the die. So if I go back to my class files here, let's imagine I create a situation here where I sample a value of 1 to 6. This sample command right here will give me a number 1 through 6 at random, where each number is equally likely. So if I just run this several times, you will see the number change. This number down in the output window here, 6, 3. Basically, if you run that thousands of times, it should be roughly equal frequency. So what I'm going to do is clear out what I had run up to this point right here and rerun everything. And then in this point right here, I'm going to redo my process. I'm going to run my chunk. And now, here, I just rolled a 3. How does that change my posterior distribution? Right? That red one that looks a little suspicious. I may have done something wrong calculation-wise, but long story short, yeah, it's all gone now. All right, this is broken, but the big picture is, going back to the slides here. Gosh, man, breaking examples. Every time that you roll a die, you're going to either change the posterior distribution by adding a number to the numerator and the denominator, or adding a number to the denominator. So basically, what you can think about is this posterior distribution that we have now is actually like the prior distribution for the next roll of the die. Right? And so every time we roll a die, we update what our belief of the probability should be, and then we do it again, and we do it again, and we do it again. Turns out that's the mechanism behind, and not to get too political here, if you know the website 538, have you seen this before? Polling data, who's leading. I'm not telling you who I'm voting for. I'm not going to tell you who to vote for. That's not what I'm doing here. Let's talk about the methodology behind it. It turns out this is a Bayesian system as well. Every time a poll comes out, these numbers are updated. These are the point estimates of the posterior distribution based on the polling data that's in the system. Now, as new polls get released, and in fact, I think it shows it down here, as new polls get released, this model gets rerun, and the new estimates get updated. And those new estimates, those updated estimates, are now prior distributions for the next analysis. So Bayesian updating is super informative, super awesome. I love it, and we're out of time, so let me just wrap up. These are some of the definitions that we discussed today. Prior distributions that have hyperparameters that can be uninformative or informative. They can be conjugate. They may not be conjugate. We have a data likelihood, and we all put all that together, and we get a posterior distribution. Next class, though, we're going to push pause on the Bayes button, and we're going to bring back our psychometric models and discuss what psychometric models are in a broad sense as well, too. So I have a few seconds left. Do you have any questions for me as I wrap up today? "10 seconds. Ask them now." I'm just kidding. I'm not going to wait 10 seconds. I don't hear any questions, so I will stop here. I will thank you for being here today, and look forward to hopefully seeing you the next time on Tuesday. So just remember, homework's out, formative assessment out. Spend 5 minutes on the formative assessment. Get your points. That works. All right, class. Thank you. Have a good rest of your week.